Welcome to Chapter 14 Physics video. This is all about waves and oscillations, and we'll have lots of interspersed videos to try to elucidate the concepts, and then there's things we can play with once we're back in class. Alright, let's get started. The first thing we're going to talk about with waves and oscillations is the fact that there are periodic events, which means they happen over and over again in a repeatable and predictable way. So anytime you have a periodic event, even if it's not a wave is a subclass of all the possible periodic events. So let's first look at some properties of periodic events. The first thing that you have that you can quantify is the period, which is how long it takes for it to happen one time. So for example, if a boxer is boxing against one of these punching bags, or an oil derrick is going up and down, or a pogo stick is bouncing up and down, there's a certain amount of time it takes for that to happen once, and then it's going to repeat over and over and over. So giving the period tells you how long it takes for one event to happen. Giving the frequency tells you the number of times it happens per second. So they're related to each other by the inverse. So if something takes 5 seconds to happen, then it happens every, then the frequency is 1/5, which means it only happens 1/5 of a time per second. In other words, it takes 5 seconds to happen once. So frequency equals 1 over time. Let me get my little color. There we go. Pen color. I guess red is good. Okay, so this is a fun little example to get started. So anytime you have a periodic event, you got the time it takes and the number of times it happens per second. Let me say real quick, the units for frequency are called hertz. That's named after a scientist. The abbreviation is Hz, and it equals cycles per second. So hertz is 1 over second, so the actual units, because cycles doesn't have an actual unit. It's like whatever it is, punches per second, or pogo stick bounces per second, or oil derrick oscillations per second, but it's always something per second. Okay, a specific type of periodic motion is called simple harmonic oscillation. This is a special example that we use a lot in physics because it's mathematically easy, or at least relatively easy compared to some more complicated stuff, and it allows us to solve some problems and apply our information and knowledge. So a specific situation for oscillatory motion or periodic motion is when the restoring force is whatever force is trying to push something back into equilibrium. When that's proportional to the displacement, then you get simple harmonic motion. So an example we've already learned about is springs. And with springs, when you stretch them out, the farther you stretch them, the more force it applies. Okay, I have a spring here to show you. At the beginning, it's easy to pull it apart, but the farther and farther you go, it requires more and more force. Okay, so the distance that you stretch it, as the distance increases here, the force needed increases as well. And it increases linearly according to the spring constant. And just to refresh your memory, what we learned about before with springs is the energy stored is 1/2 kx squared. But the simple harmonic motion part comes because there's a linear relationship between the distance stretched and the force that you have to apply. And so a result of this is that when you oscillate a spring, it's going to give you simple harmonic motion. Which means it's mathematically regular and periodic, and you can find the frequency, you can find the period, and then there will be other variables like wavelength, velocity, etc. that we'll learn about. A second example is pendulums at small angles. So when you're swinging something back and forth on a pendulum, as long as the angle is small, and by angle I mean the displacement from axis, so as it swings back and forth, if it swings all the way up to 90 degrees, then it's not going to be simple periodic motion, but at small angles, it'll be very close to simple harmonic motion. And the period of oscillation, the time it takes to swing back and forth once, is 2 pi times the square root of L over G. And this is length right here. I'll write this in over gravity. And by gravity, I mean not the force, but the value of G is 9.8 meters per second squared. So I want to prove to you that a pendulum swinging at small angles back and forth has a linear relationship between the force and the distance. So I'm going to try to do that on this slide. If you want to skip this, you can, but it's kind of cool, and I hope that you'll watch it. So I haven't done this in about a year, so bear with me if it takes me a little bit of time to get my bearings. So let's draw a pendulum here. The pendulum is going to swing down this way. Okay, so we need to look at the forces acting on it. We've got the force of gravity here, and we've got the force of tension here. Okay, and in order to follow this path right here, assuming that the string it's attached to can't stretch or compress, the forces upward that way and downward that way have to be equal and opposite. So we need to find this downward force here, and that's going to be a component of gravity. Okay, so let's call this FG perpendicular. Let's call this FG parallel. Okay, let's label this angle theta, which means this angle is also theta according to geometry, which means that FG perpendicular equals FG cos theta. And that means, of course, that FG parallel is FG sine theta. Okay, so this force right here that's kind of restoring it back to its equilibrium position is FG sine theta, okay? And so we just said the force restoring it should be proportional to the distance displaced. But in this case, the distance displaced, we're not going with linear distance, we're going with angular distance because it's angular motion. So it's the angle displaced. So right now, the restoring force is proportional to sine theta. And so you might say, well, this is not simple harmonic motion because it depends on the sine of the angle, not the angle itself. However, if theta is very, very small, then sine theta approximately equals theta. And I encourage you to check this out. And that's a caveat, only if theta is small. If theta is large, it doesn't work at all. But if theta is small, it works. So try doing, in radian mode, sine of 0.1. See what you get. Then try doing sine of 0.01. Or 0.01 and see what you get. The smaller you make the angle, the closer these two come to each other. So let me check this on my calculator real quick. I've got 0.1. We'll take sine of that. Let me go to radian mode. Here we go. 0.1 sine. That gave me 0.0998. That is really, really close. 998 out of 1,000. Close to that. Let's do 0.01 sine. This gives me... it went back to degrees. Sorry. Radians. 0.01 sine. That gave me 0.009998. So you can see this is really, really, really close. So when the angle is small and the approximation, so here I've done 0.1 radians. 0.1 radians, how much is that in degrees? Let's check real quick. 0.1 times 180 divided by pi. It's approximately 6 degrees. So if you go, even if you go sine of 0.2, it's still really close, you'll see. And so I like to say that this works pretty well up to maybe 10 or 20 degrees. If you go beyond 10 or 20 degrees worth of oscillations, the approximation will still, well, it just gets less and less accurate the bigger the angle gets. So, but in general, if you're using small angle approximation, then you can use, let me go back one slide, then you can use this formula for the period of the pendulum. All right. Resonance, here's a nice vocabulary word. So many objects in nature have a natural frequency based on their size, mass, and shape, if you will. And that natural frequency is the frequency at which the object will oscillate back and forth if you don't do anything to it. If you just say you take a kid in a swing and you pull him back and then you let go, he'll swing back and forth at some set frequency. And it depends on a lot of factors. It depends on how heavy the kid is, the way his weight is distributed, the length of the pendulum that you put him on, and things like that. And so every object has this natural frequency, and we're not going to worry about how to calculate it, but we are going to learn about resonance, which is if you apply a force periodically at the same frequency as the natural frequency of the object, its amplitude of oscillation will go very, very high. So what that means is everyday language is, if the kid is swinging back and forth in his swing, and you push him at just the right time, so you push him right when he's already going forward, the size of his swing is going to get higher and higher and higher. If you push him out of phase, or what that means is not at the right time, at a different frequency than he would naturally go, it's not going to go very far. So like take something like this. If I swing it, then I swing it even more, and then oh, this is not working. Slinky doesn't work very well. Let me see what I can do. I can do my mouse. So here we go. Oh, come on, mouse. If I swing my mouse back and forth, if I hit it, and then I hit it again, and then I hit it again, as long as I hit it at just the right time, then the amplitude's going to get much larger. But if I sit here and I go like this, and I'm hitting it at all the wrong times, then it never actually gets going very well. So the idea, the idea is when you have something in resonance, that means the frequency that you're hitting it is the same frequency it naturally would be going, and therefore all of the energy that you add to it, none of it's being wasted or counteracting its motion, and therefore the amplitude of its motion will increase. Okay, let's go over some examples of this simple introductory stuff. Suppose you stand at the beach and count 12 waves coming to shore over a span of 30 seconds. What are the period and frequency? Okay, remember the period is the number, or let's just say the time per cycle. So how much does it take? Time per cycle, we have 30 seconds for 12 waves. Well, divide those and you get 2.5 seconds. That's the time it takes for one wave. And the frequency is 1 over the period. So 1 over 2.5 seconds equals 0.4 waves per second, which is 0.4 hertz. Okay, so when you have something and you know how many you have and how much time it's taking, you can simply find the frequency and the period by dividing either time over number of cycles, or number of cycles over time, or reciprocating once you have one. Second example, a spring stores 100 joules of energy when stretched out a distance of 10 centimeters. What is the spring constant? What force is required to stretch the spring out to 100 centimeters? Okay, spring stores 100 energy. So we know we're starting with potential energy of a spring equals 1/2 kx squared. The question first is, what is the spring constant given the distance is 10 centimeters? Okay, distance is 10 centimeters, that means 0.10 meters, convert units. Potential energy is 100 joules. We're going to solve this for k, multiply both sides by 2, and then divide by x squared. Now we plug in our numbers. We get 200 divided by 0.1 squared. Dividing by 0.1 is the same as multiplying by 10. So we're going to add a 0 and add another 0 because it was squared. Newtons per meter is our units for spring constant because we plugged in all SI units. And there's the spring constant. Second question, what force is required to stretch the spring out to 20 centimeters? So here we're going to use F equals kx. We plug in our spring constant, 20,000 newtons per meter. And 20 centimeters is 0.2 meters. So 2 times 20 is 40,000 divided by 10 is 4,000 newtons. So we'll take 4,000 newtons. Another way of thinking about this is 20 centimeters is 1/5 of a meter. So we need 1/5 of this much force, because the spring constant is how much force it takes to stretch it out per 1 meter. So if you only want to stretch 1/5 of a meter, then you're only going to need to use 1/5 of the force. Okay, cool. Last example for this section. How long should a grandfather clock pendulum be if you want to have it on Earth? Well, on Earth, you probably want it to swing back and forth once per second. So we know that the period should be 1 second. And the question is, how long should it be? Well, what's the formula? The formula for pendulums is 2 pi times the square root of L over G. So we're going to need to solve for the length. To solve for the length, we should first divide by 2 pi. So T over 2 pi. Then we should get rid of the square root by squaring both sides. Okay, then we should multiply by G. And finally, we have the L all by itself. So there's our algebraic formula. Now I can plug in numbers. 1 second over 2 pi squared times gravity is 9.8 meters per second squared. And let's check our units just to be pedantic here. Seconds squared and seconds squared, those cancel out, leaving us with just meters, which is very good. So we've got 1 divided by 2 pi squared, and then times 9.8. When you type this in your calculator, be super careful. If you do 1 divided by 2, and then you hit times pi, it'll put the pi in the numerator. So make sure you hit divided by pi. And I got 0.159. Now I need to square that. 0.0253. Now I need to times that by 9.8. And I get 0.248. 0.248 meters, which is around 25 centimeters. So 25 centimeters is actually not very long. Not very long at all. Maybe, I don't know, what, less than a foot. And so when you think of a grandfather clock, you think, wow, they're usually quite long. And so what they can do in a grandfather clock, realistically, is they can use some gear ratios so that one swing will actually be 1 second. So this grandfather clock that I've proposed here would be one in which the gear that's rotating the second hand is directly connected to the motion of the pendulum, but in reality a grandfather clock has a complex mechanism of gears connecting the motion of the pendulum to the different second, minute, and hour hands inside. So it's kind of just for fun to make you think about it, but not realistic for a grandfather clock. Alright, moving right along. Real waves. So real waves, a real wave is very important, and it is a disturbance that carries energy through matter or space. The key is that it carries energy, right? It's not carrying any matter or physical objects. A wave is only carrying energy through the medium. So when you think of ocean waves, they're bringing energy to shore, but actually no water is coming in. So the water comes in and out, but the net overall flow, you know, if you come back a year later, it's not like you have a bunch of water up on the beach. It's the same amount as you had before. So the water ebbs and flows, but energy is continuously coming in. Or when you have a slinky, right? The particles move back and forth, but overall, they stay in general in the same vicinity. When the wave has finished passing through the slinky is still wherever it was. So there's two types of waves. One is transverse and one is longitudinal. And they're differentiated by the way the particles move. So in both cases, energy is passed along through the wave. But in one case, the particles themselves, the physical disturbance, is perpendicular to the direction the wave is moving. So that means the molecules themselves are moving up and down, even though the wave is moving horizontally forward. So perpendicular in some way. In a longitudinal wave, the physical disturbance, the way the particles are actually moving, is along the same direction as the wave is going. So if the wave is going sideways, the particles themselves are oscillating back and forth sideways in the same direction that the wave is going. So sound waves, slinkies, and seismic waves are all examples of longitudinal waves. Water waves, light waves, and guitar strings are all examples of transverse waves. And I've got a couple of videos, if my computer will work. So transverse waves, this is what it will look like. The physical disturbance, you can see that the hand is moving up and down. And so the particles, they move up and down only. If you zoom in and you watch this piece of metal, it only ever moves up and down, even though the energy is traveling through from here over to here. So the energy is traveling through, but the motion of the particles is only up and down, perpendicular to the wave. Watch it one more time. So zoom in on like this particle. Watch this particle. It goes up and back down, up and back down. So at no point did this particle ever move forward or backward, and by the time the energy is done passing through, you can see that the particles are all back to where they started. here's an example of a longitudinal waves. So you get compression. Sorry, my hand's in the spot. You get compression, say right here, when they send the pulse down. And this is coming back. Now they spread out. So you send a pulse, they compress, and you can see it traveling all the way down there, bounces off, and starts to come back. The video quality is not that good. Comes back. And so these slinky particles, they're moving forward and backward as the wave travels through, rather than up and down. So this is an example of a longitudinal wave. They are moving forward and backward. The net energy flow is traveling through in the direction from here to there, and then some of it bounces back, some of it goes into his hand, and then when it bounces back, it's going this way. Okay, very good. Let's keep going with the slides. That's weird. Start back at the beginning. Watch some videos we just did. Okay, mathematical waves. So of course, in your head you want to be thinking of these real conceptual waves and what they actually look like in real life. But to analyze them mathematically, there are some things we need to know about. So the graph of any periodic motion, when you draw a picture of it on your paper, it'll look like an ocean wave. It'll kind of oscillate up and down like this. And there's things we can label on it. So we can label the amplitude. We can't really label the speed, but it's an important property. As the wave travels through the medium, how fast is it going? The wavelength we can label, and the phase we can label. And so on the next slide I have a picture where I'm going to label all these things and explain them in more detail. But you can write down these definitions. And then the relationship between these variables that's really important is that you can connect the velocity to both the wavelength and the frequency. So if you have a longer wave then and a higher frequency, so it's oscillating more times per second and it's bigger, you're getting a lot more motion of the particles, and therefore the energy is being transversed through at a much higher velocity. So next slide, here I'll have an image. Pause that one if you needed to. So the amplitude here is the physical displacement from equilibrium. So equilibrium would be as if this was a flat line all the way across the bottom with no wave at all. So the amplitude is not the whole thing from the bottom to the top, it's just from the center line up to the top. Sometimes you can define what's called a peak-to-peak amplitude, but you have to be specific and label peak-to-peak. You can't just say, if you just say amplitude by itself, then you're talking about from the center up, peak-to-peak amplitude. Okay. The wavelength is the distance, or the length of one wave. So typically it's easiest if you go crest to crest, because the crest is an easy point to find. But you could just as easily go from, this point to, say, this point. That right there is also, assuming they're at the same height, is also one wavelength given by the symbol lambda. The speed you can't draw because physically this thing would be moving in time. So you just write the equation velocity equals wavelength times period. The period also you can't actually draw onto a graph because it would have to be moving in time, and so you could measure how long it takes. So, but the period is the time it takes for this. So as this whole wave travels across, if you find a point right here and you keep your eye on it, as it moves from here, it's going to move to here. Then that would be the period, the time it takes to go. And it's not actually this point that's moving. That's kind of tricky thing about waves. This point right here is actually going to come back down. But as it comes down, these points are going to go up. So this point is going to go up as this one comes back down. And then this one's going to go up. 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 And then this one's going to go up, etc. So this one's going to actually go down and then back up. But eventually this point will have gone down and will have gone right back up again. And so the time it takes for this point to, it seems like it's traveling from here over to here, but actually it's not. This point is actually traveling down and back up, and this point is traveling down and back up. But visually, if you watch it, it seems like it's moving sideways. And I encourage you to think of each particle as moving only up and down. Like, try to watch that particular particle and watch it as it goes back down, and a different particle rises to fill its spot. But the net effect of all that is that it looks like things are moving sideways. So the period is the time it seems to take to go from here to here. All right, explain the difference between transverse and longitudinal waves. In summary, transverse waves have physical disturbances, or the particle motion is perpendicular to the direction that the energy is traveling. And in longitudinal waves, the particle motion and physical disturbance is parallel, or in the same direction that the energy and wave is traveling. Okay, a jump rope is whirled 2.5 times per second. What is the period? What is the frequency? The period is the time, and the frequency is the number of times, well, I can't write today, sorry, per second. So this 2.5 times per second, that's just straight up given to us as the frequency. And let's put on units of hertz instead of cycles per second. And the time is 1 over the frequency, so that's 1 over 2.5, which is 0.4 seconds. So if something happens 2.5 times per second, then it only takes 0.4 seconds to happen once. That seems reasonable. It should match your intuition. A rope 5 meters long has 3 full waves on it, moving at a speed of 0.5 meters per second. What is the wavelength, frequency, and period? Let's draw it. So here's our rope, 5 meters long, and it has 3 full waves. 1, 2, 3. You don't have to draw perfectly, but it's good to visualize what's going on. What is the wavelength? Okay, so in 5 meters, we fit 3 waves. So the wavelength has to be 1/3 of the total distance, because you fit 3 of them on there. So 5 over 3 meters. Hopefully that makes sense. Frequency. What's the frequency? Well, the speed we know is 0.5. Okay, so we have this formula, velocity equals lambda f. So therefore, the frequency equals the velocity divided by lambda. And the speed is 0.5. And we're dividing by 5/3. So what's that going to be? The frequency, type in your calculator if you want. 3/5 of 0.5 is 0.3 hertz. So that means 0.3 times per second this wave will oscillate or seemingly travel horizontally forward. And lastly, what is the period? Okay, the period is 1 over the frequency, which is 1 over 0.3. 1 over 0.3 is the same as 10 over 3, which is 3.3 repeating seconds, if you will. So it takes 3 1/3 seconds for this one oscillation or one transverse motion of the wave. So for it to seem like this piece here has traveled over and is now this piece here, that'll take around 3.3 seconds. But what's really happening, remember, is that this particle is coming down and then back up. This particle is coming up and then back down, etc. So all the particles are oscillating. Okay. Wave behavior. So some concepts. We're almost done. Waves at boundary. So when a wave hits something, as you saw in that video of the wave, the longitudinal wave going down the slinky and then hitting someone's hand and then bouncing back. So a couple things can happen. One is reflection. The wave can hit the obstacle and bounce back. The other is transmission. So it could go through the obstacle or the object or whatever it is. And it depends a lot on the properties of the wave, what material it's made of, how much energy it has, the frequency of it, and what it's hitting, both the material, the properties of the object. So a lot of times what happens when a wave hits a border is you get a combination. So you have some of the wave reflected and some of the wave transmitted. So a simple example of that is when you shine light through a window, a lot of times there's a glare off of the window, which means some of the light is getting reflected back, but certainly some of the light is traveling through to illuminate whatever is inside. Okay, now we have 3 little concepts to end things off with, and I've got videos for each of the 3. So superposition of waves. Superposition is when you have multiple waves all on the same, say it's a slinky. Say you wiggle your end and I wiggle mine, both at the same time. What happens when the 2 waves hit each other? The displacement of the 2 waves are added together, and that gives you the net displacement. So if you lift yours up and I lift mine up, when the 2 waves hit each other, they'll go up twice as far. So that's one thing. Got a video in a second. Standing waves are the second. when the superposition of waves creates nodes and antinodes that makes waves appear to be stationary. So suppose I send a pulse up and you send a pulse up, and they travel towards each other and they hit, they're going to provide a double high pulse. That's superposition. But say we keep sending those pulses. So first we send up, then we send down, then we send up, then we send down. At one point, our two upward pulses are going to meet in the middle, and they're going to be a very high upward pulse. And then at some other point, the two downward pulses are going to meet, and they're going to be downward. So it seems like it's going to be oscillating from up to down, and the entire string can have these up-down oscillations. And you'll no longer actually realize that the waves are moving side to side. It'll look like they're just staying there, oscillating up and down. So it's like a visual effect that's kind of cool. And the nodes are the points that are stationary, and the antinodes are the points that are moving all the way up and all the way down. And the last thing is called plane waves. This has nothing to do with flying airplanes. It has to do with a geometrical plane, which is a flat two-dimensional surface. So these are parallel waves moving in the same direction. So a common example is ocean waves. So you think normally when you drop a droplet of water, drop into water, the waves expand as circles. But once you get far enough away, the front of one wave and the front of the next wave, they just seem like two parallel lines coming inward. And that's because if the radius of the circle is so large, the curvature becomes negligible, and you can think of it as a straight horizontal wave. So let's watch 3 little videos of that. Here we go.
At this point. Now the principle of superposition states that if we have 2 or more waves which meet, then the total displacement at any point is simply the sum of their individual displacements at that point. So in this scenario, if we took those 2 points, then simply the addition of those 2 points will give us a total of 20 millimeters, as we can see here in the green resultant wave. Similarly, if we took this
so I'm
point...
going to try to explain since that guy's going really slow. When you have 2 waves, the phase is really important. What the phase is it tells you if you're in the maximum and the maximum, or the minimum or the minimum. And so these phases line up. So this max here and this max here line up. So when they run into each other, the net total is going to be even bigger. Let's zoom ahead. They've got some where they don't line up quite as well. So now, let me pause it. Well, we can watch. They're kind of out of phase, which means the max here and the max here do not perfectly match up. And so instead of having the output wave be twice as big, you can see it's not actually twice as big. The amplitude only goes up to about 1.5 times as big. And ultimately, you can get them completely out of phase, like this now, where the max on one and the minimum on the other line up together, and then the minimum on the other and the max on one. And so in this case, the overall result is that they completely cancel or annihilate each other. So these are completely out of phase, and they will completely cancel. So when you hear about noise canceling headphones, that's what's happening. They're detecting the wave coming in, and they're actually playing sound out, but the sound that they play out is exactly out of phase with the sound coming in, and then the net effect of those two combined completely cancels out, and then you can't hear anything. It's really amazing. So let's talk about standing waves. Here we go. So you've all done this with slinking. We can do it in class. When you wiggle one end back and forth, the wave actually travels down, hits here, and bounces back. But the effect of those two combined makes it look like the wave is just going up and down, not traveling side to side. Then if you go even faster, you can send 2 waves down, and then 2 waves come back, and these pulses will align with each other. So the point here, like right here would be a node, and here would be a node where it's not moving, and then the antinode is moving up and down the most. So that was 3, here's 4. This is 2 full wavelengths, 1 up and down node, 1 up and down, so 2 full wavelengths. And so standing waves, they appear to not be moving, but actually the wave is just going there, coming back, and it's the superposition of the one wave going left and the one wave going right that combine to give you that effect. Last thing, a ripple tank. So these are parallel waves moving horizontally forward, and these are called plane waves. So just simple little demo that you can see what they visually look like. All right, we are just about ready to finish up. Quick summary. Sorry. Sample questions. Is it possible for a wave to be fully transmitted at a boundary, fully reflected? Give examples. Yes, it could be fully transmitted. Yes, it could be fully reflected. Let's talk about some different things in class and brainstorm ideas. What happens if two positive disturbances in a transverse wave, which means the displacement of the particle is upward, are superimposed? So one up, one up. When they two cross together, you'll get a vertical amplitude that's even larger and in the same direction. So the amplitude is larger is your correct answer there, and in the same direction. Key concepts. Okay, so when you're talking about waves and periodic motion in general, you've got the frequency, the period, the wavelength, and then the velocity is also really important. Let me write that. This equation here, velocity equals wavelength times frequency. That's your important equation relating everything together. These are your concepts. And the number one concept to remember, of course, is that waves carry energy. So waves are a transfer of energy physically from one place to another, and the way that they do that is by moving through the medium or the vacuum. Most waves require a medium to go through, but some waves can travel through a vacuum. That's pretty much it for this section on waves. In the next 2 chapters, we'll zoom in on sound waves in particular, and then light waves in particular, and analyze them in glorious detail. Alrighty, thank you much. See you in class.